In this video, we're going to discuss Dalton's Law. So Dalton's Law, also called Dalton's Law of partial pressures, tells us that the total pressure exerted by a mixture of gases, so we have more than one gas mixed together, so the total pressure exerted by a mixture of gases in a container at constant volume and constant temperature is equal to the sum of the pressures of each individual gas in the container. So we could say mathematically that the total pressure of a mixture of gas is equal to the pressure exerted by one gas plus the pressure exerted by the second gas plus the pressure exerted by the third, fourth, fifth, etc. The pressures exerted by each individual gas in the mixture is called the partial pressure. So if we have the total pressure and gas number one exerts some pressure, we would say that's the partial pressure of that gas. And gas 2 also has a partial pressure. So the total pressure is the sum of the partial pressures of the gases in that mixture. So here in this illustration, we have two gases. The first gas, let's say its partial pressure is 2 atmospheres. The second gas, its partial pressure is 4 atmospheres. If we combine these two gases, keeping the volume and temperature constant, well, then the pressure of the mixture, Dalton's law tells us that the pressure of the mixture of gases is going to be equal to the partial pressure of gas 1 plus the partial pressure of gas 2. In other words, the total pressure, when we mix gas 1 and gas 2, the total pressure would be 2 atmospheres plus 4 atmospheres, or 6 atmospheres of pressure. Now the partial pressures, let's talk about that in a little more detail. The partial pressure of a gas in a mixture is related to the amount or the number of moles of that gas. So let's say that we have a mixture of two gases. Right here we have a mixture of gas A and B. Okay? And we have twice as many moles of gas A. You can see we have more moles of gas A, twice as many moles of gas A as we do gas B. So we mix those together, and the partial pressure of gas A in the mixture will be twice the partial pressure of gas B. So the more moles of a gas that you have, the greater the partial pressure of that gas. Now, we want to be able to mathematically calculate the partial pressure of a gas in a mixture. We can calculate the partial pressure as follows, as you can see in this equation, where PA, that's the partial pressure of some gas. It could be oxygen, nitrogen, methane. So this is the partial pressure of the gas that we're interested in. This X, or chi, A, is the mole fraction of gas A. We'll explain that more in just a minute. And P subtotal is the total pressure of the mixture of gases. So we can calculate the partial pressure of a gas by taking the mole fraction of that gas times the total pressure of the mixture. So let's talk a little bit about this new term, mole fraction. Let's define that. The mole fraction of a gas in a mixture is equal to the number of moles of that gas divided by the total moles of gas in that mixture. Now here we have Na plus Nb. This would be the moles of gas A plus gas B, but you may have 3, 4, 5 different gases. So this is the total moles of the gas in the mixture, and on top we have the number of moles of the gas that we're interested in. So let's take a very simple problem here to illustrate this. Let's say we had 4 moles of gas A, and we mixed it with 2 moles of gas B. So now we have our mixture, 4 moles of gas A and 2 moles of gas B. What is the mole fraction of gas B in this mixture? Well, simply put, we would take, to calculate the mole fraction, we said we had 2 moles of gas B, and we have 4 moles of A and 2 moles of B. So our total moles are 6 moles. So we just divide the moles of gas B by the total moles, in this case 2 divided by 6, and we would get 0.333. And the mole fraction doesn't have any units, so it's a unitless value. Let's take a look at a problem to help us illustrate calculating both mole fractions and partial pressures. Okay, read through the question, pause the video, and then try to solve it. Okay, give it a try. Okay, so It says determine the mole fractions and partial pressures of a mixture of gas. We have carbon dioxide, methane, and helium, and we have the moles of each. So first, let's calculate the mole fraction of each gas. Okay. So let's calculate our total moles. We add the moles of carbon dioxide plus the moles of methane plus the moles of helium, and we get our total moles, 5.05 moles. To calculate the mole fraction for each gas, we just take the moles of that gas divided by the total moles. So you can see here for carbon dioxide, we took 0.250 moles of carbon dioxide divided by the total moles, and you can see the mole fraction here. So the more moles of the gas we have, the larger its mole fraction. Appreciate that. We have more moles of helium, so the mole fraction of helium is greater. In other words, you can see this is really kind of like a percentage. The moles of helium, the mixture contains about 69.5% helium, about 4.95% carbon dioxide. So we have our mole fractions. Now we want to calculate the partial pressure of each gas. Well, we said to calculate the partial pressure, we simply take the mole fraction for the gas times the total pressure, which was given. So we take the total pressure times the mole fraction for carbon dioxide, 0.286 atmospheres. In this case, we have units of atmospheres. So you can see the partial pressures of each gas. Now, Dalton's law also tells us if we add these together, we should get the total pressure. So we can kind of check our work here. If we add the partial pressures together, we should get 5.78 atmospheres. Also, please notice that the greater the mole fraction, the greater the partial pressure exerted by that gas. Again, as we mentioned before, the partial pressure is related to the moles of gas in the mixture. So that was a fairly simple problem. Take a look at this one. This one's a little more challenging, but read through the question, pause the video, and give it your best try. Okay, so here we have a 10-liter steel container at 90 degrees Celsius contains a mixture of gases. We're given the mass of each gas, hydrogen, nitrogen, and ammonia. What is the total pressure and the partial pressures of each gas? So here, this one's a little tricky. We're not given the total pressure or the partial pressures, but we are given the volume. So we know our volume. We are given the temperature in Celsius, but we can calculate that, convert that into Kelvin, and we can, given the grams of each, we can calculate the moles of the gas or the moles of the mixture. So using PV equals nRT, that's going to allow us to calculate our total pressure. Okay. So let me show you how I did this. There's a couple of other ways, so you might, if you did it a different way, that's okay. But the first thing I wanted to do is calculate the moles of each gas. I took the mass, the grams, and divided it by the molar mass to get the moles of hydrogen, nitrogen, and ammonia. Now I added the moles together, the moles of each, in order to get the total moles of my mixture. That's going to allow me to calculate the mole fraction. Okay, so let's calculate the mole fraction. We took the moles of each gas, which we just calculated, divided by the total moles, and we get, again, the mole fraction for each gas. Now to calculate the partial pressures, we need the total pressure. So to do that, I used PV equals nRT as I said, and I solved for P. Now here, for N, I'm using the total moles. Okay, so I want the total pressure, so I'm using the total moles in my equation. So the total moles times RT, again, we must have that in Kelvin, divided by our volume gives us a total pressure of 25.27 atmospheres. Now, it's an easy matter once we get that to take our mole fraction of each gas times the total pressure, and that's going to give me my partial pressures of hydrogen, nitrogen, and ammonia. Now, there is another way that you could have done this. You could have taken the number of moles of, say, nitrogen and plugged it in here, and that would have given you the partial pressure of nitrogen. And then taken the number of moles of ammonia, plug that in to calculate the partial pressure of ammonia. So you could have used PV equals nRT using the moles for each gas to calculate the partial pressure for that gas, and then add the partial pressures together to get the total pressure. That's a perfectly acceptable way to solve this problem as well. So be sure that you understand Dalton's Law and you can solve problems which involve mixtures of gases. So again, appreciate that Dalton's Law is only used to solve problems related to mixtures of gases.